Swayam Prabha. Digital India. Educated India.
So, welcome to the 18th lecture of the NPTEL course on cryogenic engineering. We have done various topics till now, and the broad topics we can classify them as: first, the introduction to cryogenic engineering. We studied the properties of different cryogens and therefore properties of cryogenic fluids. Then we studied the properties of materials at cryogenic temperature. And the last topic which we covered was gas liquefaction and refrigeration system. Having done all these 4 topics, now I will be changing some gears and we will be going to now gas separation, which is a very important topic of cryogenic engineering. Having liquefied gases together and air being a mixture of various gases, whenever we liquefy air, we got a lot of gases in liquefied form in air, and now we have to separate oxygen, nitrogen and other gases, maybe argon, from liquid air, and therefore, we have to use a gas separation technique. And this is the most important thing, because gases are needed by every industry nowadays, and therefore, this topic has got a very special relevance from users point of view, from gas users point of view. So, the topic is now gas separation. What we are going to study under this are different subtopics, which are basics of gas separation, then ideal gas separation system. Just as we got an ideal system for every system to compare with, we got an ideal gas separation system also. Then we will study properties of mixture and the governing laws. Now, as you possibly know that we got several laws which govern the mixtures, and they help us basically in understanding the partial pressure business and the total pressure and their relationship, and they are very important to analyze these mixtures so as to get the properties of mixtures at different temperatures and pressures. Then we will study principles of gas separation in broad, and then separation process itself, the rectification and plate calculation. So, plate calculations actually essentially mean that there is a column which has got a lot of plates, and we have to calculate number of plates involved in that. So, this is a very important topic, and which involves, actually it covers a bit of chemical engineering also, because it has got some mass transfer aspects associated with it. We will keep it of course for mechanical engineers, however, and therefore, from this point of view I am basically going to cover this topic from mechanical engineering point of view. The current topic will be covered in around 7 to 10 lectures, just as we had liquefaction in 7 to 10 lectures. Similarly, as we proceed ahead, the number of lectures possibly will be around 7 to 10. And then tutorials and assignments are also included at the end of each lecture. So, in this topic, what we are going to learn is the outline of today's lecture will be the basics of gas separation, in which we will study some gas separation methods, and then we will find what is the ideal gas separation system, and we will find what is the ideal work requirement for an ideal gas separation system. These 2 subtopics will be considered, will be taught in this lecture of first lecture of gas separation. Right. As mentioned earlier, the cryogenic industry is huge owing to the various application of the cryogens both in liquid and gaseous states. For example, the use of inert gases like argon in chemical and welding industries has increased in the recent past. Basically, I am highlighting the utility of these gases in various industries. Liquid nitrogen is used as pre-coolant in most of the cryogenic systems. Also, cryogens like liquid oxygen, liquid hydrogen are used in rocket propulsion. In the recent past, liquid hydrogen is being considered as a fuel in an automobile. The production of ammonia in RCF industry, for example, the fertilizer industry, requires separation of purge gases like nitrogen, argon and other inert gases. This production has to be done at cryogenic temperature, and therefore, separation of gases play a very important role in fertilizer industry also. For most practical purposes, air is considered as a mixture of 78% nitrogen, 21% oxygen and 1% argon. So, If we want to use nitrogen, oxygen and argon, we have to basically separate them out from air. The other ingredients are helium, neon, krypton, which occur in negligible quantities. So, normally as far as helium, neon, krypton are considered, the to take them out from air becomes rather difficult. So, normally air will be used to obtain nitrogen, oxygen and argon, which are abundantly required in the industries. So, air serves as a raw material. Air is a raw material for the production of most of the gases, and the process of separation of the gas mixture into its individual component is called gas separation. That is what normally we define as. In other words, this topic of gas separation deals with separation of various gas mixtures and their purification. Now, how do we separate gas mixture? There are various techniques available. We will just touch upon those techniques and then we will come down to the technique of cryogenic gas separation. So, what are these different techniques to separate various constituents of a gas mixture? One is using synthetic membrane. We will see each of these techniques in brief to understand how the separation occurs using synthetic membranes. The second technique is adsorption, which is a physical phenomena, as possibly most of you know. The absorption, other technique of separation of a gas mixture, and then the cryogenic distillation. So, broadly there are 4 methodologies, of which the first 3 are normally at room temperature, while the last one is cryogenic distillation or separation at cryogenic temperature or at low temperature. So, we will first study what these 3 techniques are, and then we would go to cryogenic distillation in detail. So, let us see what synthetic membrane mean and how does synthetic membrane separate a gas mixture. Synthetic membranes are the porous media which allows only a certain gas molecules to pass through. So, very simple, all right. So, you can see from this figure. This figure shows there is a membrane in some cylinder, and this membrane allows to separate a mixture of A and B molecules or a mixture of A and B components of gases, and there is the piston which you see from the left side. Okay. Synthetic membranes are the porous media which allows only a certain gas molecules to pass through. The membrane in the figure allows only gas A to pass, and hence separation occurs. So, in this particular figure, what you say, this membrane allows only A to pass through it, while B cannot pass through it. So, what will happen? If I go on pushing this piston on the right side, the A will pass through the membrane, and on the right side of A, as you can see, right side of membrane, what you can see is only the component A. That means, only the gas molecule with A gas will come through this membrane, while the B gas would be always on the left side, okay, because B can't pass through the synthetic membrane. For example, thin sheet of palladium allows only hydrogen gas to pass through. So, if I use palladium material as membrane material and then have a mixture of various gases in which one of the components is hydrogen, and then if I use such kind of a arrangement, only hydrogen will be in this particular location where A is right now, because this membrane will allow only hydrogen to pass through it, while other gas members will not be able to pass through it, all right. So, this is a way the membranes can be used. They are being used, various membranes, they got a preferential treatment, preferential passage for a particular gas, and according to which they could be used. The second technique is adsorption. So, adsorption is a physical process in which only a certain kind of gas molecules are adhered to the adsorbing surface. Most of you know this adsorbent, that you got a surface phenomena, and if you got A and B gases, then only one of the gases can adhere to the mixture, or it can get adsorbed on this adsorbent, while other gas cannot. So, adsorbate in the figure adheres only gas A. So, this is adsorbate, and the gas only can get adsorbed on the surface of this adsorbate. So, it allows only A to adhere to the surface, while B cannot adhere to the surface. In a way, therefore, a mixture of A and B will get separated. A will adhere to the gas adsorbate surface, while B will be freely lying over here, and then in a way this is separation of gases A and B. So, the adsorbate in the figure adheres only gas A to the surface, hence the separation occurs. So, what you can see here, the layer here will have only A components adhered to it, while all the B components eventually will be, all the A's would be getting adsorbed, while B would remain there, meaning which A and B have got separated. For example, finely divided nickel adsorbs hydrogen on its surface. So, if I want to separate hydrogen, I can use nickel as an adsorbate, and hydrogen will get adsorbed on the surface of this nickel. Second one is absorption, which we know that we got a sponge basically, all right. So, we know that absorption is a chemical process in which substance in one physical state is taken into other substance at a different physical state. So, it's basically solid can take liquid or solid can take gas, and one physical state is taken into other substance at a different physical state. For example, liquid being absorbed by a solid or gases being absorbed by a liquid. So, what is the example? When an incoming stream of containing carbon dioxide is passed through a solution of sodium hydroxide, the latter absorbs the gas and hence decreases the CO2 content in the outgoing stream. So, if I got a sodium hydroxide will absorb CO2, there will actually a chemical reaction will happen between sodium hydroxide and carbon dioxide, meaning which if an incoming stream has CO2, the quantity of CO2 can be lessened from this mixture and in a way separation occurs. So, if I got a sufficient quantity of sodium hydroxide, all the CO2 from the incoming gases can be removed, because sodium hydroxide will absorb CO2, there will be chemical reaction and maybe some other compounds get formed during this chemical reaction. In a way, this is a method of separation, and therefore, this absorption is used abundantly in the chemical reaction. Hence, this chemical process helps in the separation of the mixture. So, in this case, I am removing CO2 from the mixture by absorbing CO2 by sodium hydroxide. So, having done membrane, adsorption and absorption, having understood the basics of this, now let us come to the distillation. Now, distillation is a process of separation based on differences in volatilities or the boiling points. So, I got different gases, and all these different gases have got their boiling points and they are different. Depending on the characteristics of these gases, the boiling points will be decided, and there is a unique boiling point for each gas. Choosing these volatilities or the differences in the boiling point, we have got a process that is called as distillation. So, here you can see that this is something called, schematically I have shown here something called a distillation column, to which a mixture of A and B, gas A has got a different boiling point, gas B has got a different boiling point, and if this mixture enters this distillation column, what you can see is the mixture A is at the bottom at the end and mixture B at the top. So, one which has got a high boiling point of around 90 Kelvin, which is oxygen boiling point, you will have it at the bottom, and the liquid you will get for gas A at the bottom, and one can convert this liquid to gas if one wants gas, or one can get this liquid, one wants liquid A also. Similarly, on the top what you get is a lower temperature, here the Q is removed, here the Q is added. So, you can see that Q in and Q out over here. The low temperature boiling point gas, for example, nitrogen, which has got a boiling point of 77 Kelvin, will be obtained at the top of this distillation column. This is just a schematic. So, a mixture of A and B enters the column, and at the end this is now a cryogenic separation, because the boiling points of these two gases A and B are different, they can get separated. A is coming at the bottom, B is going at the top of this column. So, if the process of distillation occurs at cryogenic temperature, this process is called as cryogenic distillation. The commercial production of gases like oxygen, nitrogen, argon, neon, krypton and xenon are obtained by cryogenic distillation of liquid air. So, liquid air is actually the source of all these gases, and therefore, if you liquefy air, that means all these gases are in the liquefied form in the mixture, and this mixture can be fed to the column, and according to the difference in the boiling points of these gases, they can be separated. And this is what we are going to see in the coming slides and coming lectures. The separation of a gas, separation of a mixture can be done at both room temperature and at cryogenic temperature, as we just saw. For example, in the case of air, the following processes are possible. So, I just showed an example where the cryogenic distillation is done, but there is a possibility that one can do this separation at room temperature also. So, if I got air at 300 Kelvin, I can liquefy this air at 78 Kelvin, which is the boiling point of air, and from where I can get liquid oxygen and liquid nitrogen, which have got boiling point of 90 Kelvin and 77 Kelvin. And therefore, because this separation is occurring at lower temperature, first I am liquefying air and then I am separating the two gases from liquid air, I call this process as cryogenic separation. The other process is now, I have got air first at 300 Kelvin, and first at room temperature itself, at 300 Kelvin itself, I am dividing or I am separating this mixture, assuming that air is a mixture of nitrogen and oxygen only. I got oxygen at 300 Kelvin and I got nitrogen at 300 Kelvin. That means I am doing this separation of air at room temperature itself, and then I get oxygen at 90 Kelvin and nitrogen at 77 Kelvin if I want liquid nitrogen and liquid oxygen. But you can see from here that the separation has occurred at room temperature, for which I use special techniques called pressure swing adsorption, temperature swing adsorption, and they are basically adsorption techniques of separating oxygen and nitrogen. These are more widely used these days. It has got its plus points and negative points. Similarly, cryogenic separation has got its plus point and negative points. Some of the advantages of cryogenic separation over room temperature separation are: the separation at lower temperature is most economical. We will find later that as the separation temperature decreases, the power input requirement or the work of separation requirement lessens. So, here we can understand that. There is an increased difference in the boiling point of the ingredients. So, we can do that separation is effective because of the difference in volatilities. A large quantity of the gases can be separated in the cryogenic distillation, and a high purity of the gas can be obtained. If we do the separation at lower temperature, we can get high purity of the gas. We can obtain high purity of the gas at cryogenic temperature. These are the certain advantages of cryogenic separation. Let us understand, is gas mixing is a reversible process? What do I mean by that? That means if I mix the gas, can I unmix it and can I mix them together? So, meaning which, is this process a reversible process? So, consider a closed chamber filled with gas A and gas B as shown here, and initially the gases are separated by impervious wall. That means A is here and B is here, and there is the impervious wall which will not allow A and B to pass through. They are separate entities in this chamber. If the wall is removed now, the gases would mix. So, suppose I remove this wall, you will find that A and B are together. Now, if I go back and put this wall again, can I get A and B separated? Is it possible? This is not possible, and therefore, I will say that the replacement of the wall would not result in separation of gas, and therefore, I can claim that this process is not reversible. It is clear that the mixing of two different gases is an irreversible process, because unmixing or separation of the mixture requires work input. I have to do some work on this, then only I can unmix the gas. The system in which all the processes are reversible is called ideal system, as you know this. So, mixing and unmixing, if it is possible, if it is a reversible process, then I will call this ideal separation system. Although in reality, such a system does not exist, a system can be conceived. As you know that every time normally we deal with an ideal system of separation, and therefore, we can conceive such a system wherein if I calculate work of separation or work of mixing and unmixing, I have to first conceive an ideal system. I am going to conceive a system conceived to serve the required purpose as explained in the next slide. So, I am basically having an ideal system of gas separation now. And how does this work, ideal gas separation system? So, consider a closed chamber filled with a mixture of gas A and gas B as shown over here, and there are two pistons, one is red and one is black, and again I got a mixture of gas A and gas B. These two pistons as shown by arrows can be moved inside and can be taken outside also. The temperature of this gas mixture is Tm, the pressure of this gas mixture is Pm. The temperature and the mixture pressure are Tm and Pm respectively. The partial pressure of gas A and gas B are P1A and P1B. Depending on the amount of gas A and gas B, we got a partial pressure of gas A and gas B termed as P1A and P1B. The chamber has two frictionless opposing pistons made from semi-permeable membrane as shown in the figure. So, these are not only pistons, they are also membranes, and they are semi-permeable membrane, meaning which they allow only one type of gas A or B to pass through it, as we had seen earlier. So, we got a piston which will compress this gas, at the same time it will separate one of the components of this mixture. As seen earlier, a semi-permeable membrane is a film which allows only one kind of gas to pass through, but not the other. Alright. So, this membrane will allow only one type of gas to pass through it. The left piston, which is a red, it will allow only gas A to pass through it, and it will not allow the gas B to pass through it. Alright. So, basically when I start pressing this left piston to the right, it will let A go through it, but it will not allow B to go through it. Similarly, when I press B on the left side, it will allow only B to pass through it, and it will not allow A to pass through it. Similarly, the right piston allows only gas B to pass through, but not gas A. This is what we call it a semi-permeable membrane working like a piston in this closed chamber. So, as if I go on pressing these two membranes or pistons, you can find the separation has started occurring. So, I am getting on the left side of the membrane only A, and I am getting right side of this green piston or green membrane only the component B. So, when I basically reach both the pistons reach together, A and B would get separated. When both the pistons are moved inward, the mixture is separated and it would look like this. Understood? So, I got a mixture A, I got a gas A and gas B separated from mixture of gases A and B as seen here. Since the processes are reversible, we are claiming this particular process to be reversible. What should happen? The system interacts with the surroundings to maintain a constant temperature. So, all these processes are happening at temperature being constant Tm. So, what I am doing basically? I am pushing this piston B and piston A inwards. So, I have to do some work W A and W B respectively, and at the same time, because the compression process is occurring, some QR is being released, some heat generated is being released, so that the temperature Tm is maintained. I am saying that the temperature Tm is all through constant, and because of this QR, the temperature Tm is being maintained. Because of this interaction with the surrounding, the constant temperature is maintained. The work of separation is the work required to compress each gas from its partial pressure P1A to Pm and P1B to Pm. The piston A is compressing the gas B, while the piston B is compressing the gas A. Alright. So, Wb is the work done on the piston B, while Wa is the work done on piston A. And what is this compressing? Compressing gas B from partial pressure P1B to the mixture pressure Pm, and the whole process is carried out at temperature Tm. So, here you can see that the gases A and B are being separated, have been separated here. Since the left piston is permeable to gas A, the gas A exerts no pressure on the left piston. Alright, when this piston moves, the pressure is exerted on this piston by gas B and not by gas A. Similarly, the gas B exerts no pressure on the right piston, it will be gas A which will exert pressure. Gas B will just pass through this, gas A just passes through this. When both the pistons are moved inward, the mixture is separated at constant temperature Tm, because we are calling this the temperature remaining constant in this case. Alright, so this is a separated gases A and B. The pressure here is Pm and temperature being Tm, the pressure being Pm and the temperature being Tm. The entire processes are assumed to be reversible. So, now I find that the mixture has been separated, but because this process is reversible now, this process should also reach back to the earlier point where it started from. The process is reversed due to the difference in the concentration of gas A and gas B. So, slowly gas A will start diffusing through piston A and gas B will start diffusing through the piston B, because they are semi-permeable membrane. And slowly the concentration balance will get created. Slowly there will be difference in concentration on the left side of the piston and right side of the piston for gas A as well, piston A as well as for piston B. And slowly the process of diffusion will start, and slowly this piston would start moving back. It will take a lot of time, but because the process is being reversible, the process would start, and therefore, meaning which the gas A will start getting combined with gas B. That means the mixing process will start. A reversible process of mixing will get start. First we have unmixed or separated A and B, but now slowly gas A will start coming in, gas B start coming in, and process of mixing will get started. Hence, the mixing of the gases would move the pistons away and produce work. So, here with time the gas A will start coming in the gap between piston A and B, and it will start pushing this piston A back and piston B back. That means, the work will now get produced by the system. Earlier we had put in the work, we had work done on the system WA plus WB. Now, the same work will get created by on piston A and piston B by the gas, because now the gas is going to work on the piston. So, here what you can see is piston A is moved back, piston B is moved back, and slowly a mixture of A and B getting formed in this space. So, this is basically the reversible process, which is what you are seeing here occurring now. The work produced in this mixing process is same as the work done to separate at constant temperature Tm. The final condition is system with a mixture of gas A and B at Pm and Tm. So, ultimately I get a mixture of gas A and B at Pm and Tm. So, what you see here now, in which again now, because the work is kind of expansion of the gases, I am supplying QR, the temperature being kept constant, the surrounding is now putting some heat inside, so that the Tm is kept constant, temperature is maintained, and Wa and Wb is the work done by the system, work which is produced by the system during mixing. Also, the partial pressure of gas A and gas B will be P1A to P1B. So, ultimately in this mixture, it will have partial pressure of P1A and P1B as it was previously. So, ultimately I will get now a mixture of gases. First I had unmixed the mixture, and again mixture has occurred automatically. And if I put in the work Wa and Wb, again the process would repeat. So, this is what we call as a reversible process. We are conceiving a system, and wherein we can call this particular process as a reversible process of gas separation. So, this is my initial condition when I got a mixture A and mixture B, gas A and gas B in a mixture form. This is my final condition where I got mixture separated in gas A and gas B. The moment I say they are reversible process, I should have the arrows like this also. So, I can go from initial to final and final to initial. In both the cases, temperature Tm is maintained constant. So, basically the gas A is getting compressed from P1A to Pm when I am pushing this piston, and gas B is getting compressed from P1B or the partial pressure of B to Pm. In other words, thermodynamically each gas is compressed reversibly and isothermally from its partial pressure to the mixture pressure. So, what I am doing basically while separating this mixture, I am compressing reversibly and isothermally gas A and gas B from its respective partial pressure to the mixture pressure. This is what basically I am doing in separating this gas mixture. In order to understand the process of compression, say gas A from P1A to Pm, the following analysis is done. Now, basically I would like to calculate the work of separation of gas A and gas B. When I say work of compression, is nothing but work of separation, and this will give me ideal work of separation. This is what I am going to calculate now. So, now let us see the ideal separation system. Let us do the calculations to understand what is the work of separation if one goes for a ideal separation system. Let the molecular weight of gas A and gas B be denoted as mole A and mole B respectively. The number of moles of gas A will be given by, this is very simple mixture formulae which I am going to just kind of revise and go ahead. So, if I want to calculate number of moles, it will depend on how much grams of gas A is there divided by its molecular weight, that will give me moles. So, Na is a moles of gas A in a mixture of A and B. So, Na will be given as Ma upon molecular weight of A. Similarly, Nb will give the moles of B, that is Mb upon molecular weight of B. The total number of moles in the mixture Nm, suppose the mixture number of moles in a mixture are Nm, you know Nm is equal to Na plus Nb. And the ratios now I call as Ya, which is basically mole fraction of gas A, Yb is a mole fraction of gas B. The mole fraction of gas A is called Ya, which is Na upon Nm, and Yb is Nb upon Nm. Okay. So, Yb and Ya are basically the mole fractions of gas B and gas A respectively. Now, this is what our initial condition was of A and B when they were a mixture at Tm and temperature of Tm and Pm pressure, and the partial pressure were P1A and P1B. The corresponding volume occupied by the mixture was V total, and I can apply now simple gas laws, which is P1A into V total. This is for a gas law, ideal gas law for gas A, and similarly I will have ideal gas law for gas B. So, what is the pressure of gas A? P1A into V total is equal to Na RT, where R in this format is what is we call as a universal gas constant. Similarly, I will write the same equation for gas B also. If I combine them together, P1A plus P1B into V total is equal to Na plus Nm Nb Rtm. So, Pv is equal to Nrt is basically I am applying for gas A and gas B and also a mixture of gas A plus gas B. Note that the volumes are always the same, because A and B together are occupying the same volume and individually also are occupying the same volume. meaning which P1A plus P1B is equal to Pm. That is what we have been talking about. And now I say final, when I got a separation has occurred and I got now particular volume of Va associated with gas A and particular volume of Vb associated with gas B, while the temperature is same as Tm, and now the pressure of the gas A here is Pm, the pressure of the gas B here in Vb volume is Pm. So, again I apply the gas law, the ideal gas law for gas A and gas B. Now, the pressure of gas A in this volume of Va is equal to Pm. So, Pv is equal to nRT for gas A, which is Pm into Va is equal to nART. Same thing I do for gas B. And if I now see that, if I divide this by this, what I get is Va upon Vb. This will basically give the ratio of how much volume is occupied by Va and Vb. It will basically give a function depending on what is the ratio of molecules of Na, moles of Na divided by moles of Nb. All right. So, how many moles of Na A are there, how many moles of B will decide what is my Va and Vb are. The volume occupied by each of the gas is directly proportional to the number of moles. That is what we have just seen. From the earlier lectures, the work requirement for unit mass of gas compressed isothermally is given by Wi by m dot, which is Tm into S1 minus S2 minus H1 minus H2. This is what we had done. We had derived this equation in the gas liquefaction cycle. So, basically Wi is the ideal work done of compression basically, because as we earlier said, as we earlier pointed out, that separation is nothing but compressing the gas from partial pressure to the mixture pressure, P1A to Pm or P1B to Pm. So, Wi by m is equal to Tm into S1 minus S2, which is entropy difference minus H1 minus H2 enthalpy difference. The net ideal work requirement of the separation process is the sum of the ideal work requirement for gas A and gas B. So, I can write mathematically that Wi is equal to Wia plus Wib. The total work of separation is equal to work of separation of gas A plus work of separation of gas B, and dividing by m dot I get this Wi by mm divided by Wia mm plus Wib divided by mm is nothing but the mass of the mixture. So, this is what we have just seen. The total mass of the mixture is and is the sum of gas A and gas B. We can write is equal to nothing but Ma plus Mb. Absolutely clear till now. Rearranging the terms, now I am just writing these terms in a different format as given here. So, Wi by mm is equal to Wi upon Ma. This is nothing but work of separation for gas A multiplied by Ma by mm plus work separation of gas B divided by Mb, Wib upon Mb into Mb by mm. So, I am just writing as Wi Ma by Ma gets cancelled, what I get is Wi by which is what you see here. So, what I am basically writing this expression as Wi by is equal to work of separation of Ma into this component plus work of separation of B into this component. Here Ma and Mb are the masses of gas A and gas B respectively. So, this is what we have just seen. Now, I can write an expression for Wi by Ma also. The work requirement for each of the individual gas is given by following equation. So, Wi upon Ma is equal to Tm into S1A minus S2A minus H1A minus H2A. This is the expression we have just seen of work of separation when I compress the gas from 1A to 2A position for gas A, and similarly I can write the same expression for gas B also. Substituting and rearranging the term, if I put this value over in this equation, I will get a very long equation. So, substituting this by this and substituting Wib upon Mb by this, what I get is this very big expression over here. Tm is the temperature of mixture which is remaining constant. Now, let us find some expression for this entropy difference and enthalpy difference. So, this is my expression. What you can see from here that this is Tm, which is a mixture temperature figuring out here, and this is a work of separation of the gas, and as you can see that if the Tm is lowered or the mixture temperature is lowered, Wi by m will be, the work of separation will be very less, and that shows directly that if the temperature is very low or in the cryogenic temperature region, the work of separation will be very, very less. It is clear that work requirement decreases with the decrease in temperature. Hence, the separation of mixture at the cryogenic temperature is most economical, and one point is proved mathematically from here that if Tm is less, if the mixture temperature is less, the work of separation will be very, very less. The subscripts 1 and 2 denotes the initial and the final condition respectively. What does it mean? What is the condition 1? It means that for each gas, S1 and H1 are at the partial pressure before separation, because each gas is being compressed from its partial pressure to mixture pressure. So, one condition, the S1 and H1 are basically conditions prevailing at partial pressure before separation, while S2 and H2 are at the mixture pressure, because the gases are being compressed from their partial pressures to the mixture pressure after the separation of the mixture. For the sake of understanding, let us first evaluate the entropy and enthalpy terms for this. So, let us see if you could substitute by some simple expression for this enthalpy and entropy differences for gas A and gas B respectively. For an ideal gas, the specific entropy S and specific enthalpy H are expressed as below. So, S is equal to Cp log T minus R log P plus some reference entropy term. Similarly, enthalpy is equal to Cp into T plus this reference enthalpy term basically is any temperature, any pressure one can select, and what we mean to say that it should remain constant throughout calculations, where SR and HR are some reference values. They could be at 77 Kelvin or boiling point or 1 bar and 0 Kelvin or whatever, because there are various temperature entropy diagram which can have different references values, and what we mean to say that whenever we refer to such different diagrams, we should keep the same reference values. Hence, S and H for each gas A are given as, if I put now this general expression for gas A, I will get this expression, while similarly I will get for S2A, that is after at a temperature Tm and mixture Pm, I will get this expression. All right. Similarly, enthalpy values at 1A and 2A conditions are given by this expression. The entropy and enthalpy terms are given. What I want to basically find out is the difference in S1A and S2A minus H1A and H2A, and if I put those values over here, I get this expression. This is for entropy difference and this is for enthalpy difference. And if you see now, because the temperatures remaining same from 1A to 2A, these terms can get cancelled. So, this term will get cancelled. Similarly, the reference values are same, they will get cancelled over here. And in this case, again the temperatures remaining constant, these terms will get cancelled. So, what remains here basically RA log P1 by P1A minus sign plus RA log Pm, and it is basically nothing but logarithmic difference, which is nothing but RA into log Pm upon P1A. So, entire S1A minus S2A minus enthalpy difference gets reduced to RA log Pm upon P1A. Similarly, I can do the same thing for gas B, and I will get expression S1B minus S2B minus H1B minus H2B is equal to RB log Pm upon P1B. So, I have done a major calculations, and whatever expressions we have first got to calculate the work of separation, wherein this entropy difference and enthalpy difference figure, this complete term now will get replaced by this. For gas A and gas B, complete term will get replaced by this. Now, let us find what is this Pm upon P1A mean, or what is Pm upon P1B mean. So, this is what we got an expression now, this is what we got for gas B. So, I can put this expression back in my Wi by mm is equal to this, and my expression will be now replace this term by this in this expression and replace this enthalpy entropy difference by this, and my final expression therefore will be like this. So, I get Wi upon mm is equal to Tm into Ma upon mm like this. This entire term get replaced by Ra into log Pm by A plus Mb upon mm comes over here, and this entire term of enthalpy and entropy difference get replaced by Rb log Pm by P1B. So, my expression becomes very simple, and now I would like to understand what is my Pm upon P1A is, what is my MAR upon MM is. I would like to understand those quantities. Since the process occurs at constant volume Vm using ideal gas equation, which is Pv is equal to nRT, I can write this expression which we have done earlier. Pm into Vm is equal to Nm RTm. So, I can write the same expression for gas A and gas B. So, this is a mixture equation for the mixture, equation for gas A and equation for gas B. Dividing one over the other, what we get is Pm Vm upon P1A Vm is equal to Nm RTm upon Na RTm. RTm and RTm gets cancelled, Vm and V get cancelled. So, Pm upon P1A is equal to Nm upon Na is equal to 1 by Ya. We know that Na upon Nm basically moles of A divided by moles of mixture is equal to mole fractions of gas A. So, Pm upon P1 ultimately gets reduced to 1 upon Ya. Similarly, I can do for ratio of mixture and gas B also, and I get the same thing, that Pm upon P1B is nothing but Nm upon Nb is equal to 1 upon Yb. This is what we get from here now. So, I have got a ratio of P1 by P1A figuring in the early expression. I can replace that by 1 by Ya, where Ya and Yb are the mole fractions of gas A and gas B respectively. The ideal gas equation can also be expressed in terms of mass of the gas as shown below. So, I can write this expression PV is equal to nRT for gas mixture, gas A and gas B. I can write this Nm or the molar fraction as the mass of gas, mass of mixture divided by molecular weight of mixture. This is basically definition of Nm. I am just replacing this Nm by mass of mm upon molecular weight of m. So, PmVm is equal to mm upon molecular weight of m RTM, and same thing I am doing it now for gas A and same thing I am doing for gas B. Here Ma upon molecular weight of A, here Mb upon molecular weight of B will figure. So, why I am doing all these things? Basically, I know now that PmVm is equal to mmRT. Now, here R by molecular weight of m is nothing but now specific gas constant. Here universal gas constant R divided by molecular weight of A is specific gas constant of A, and here also similarly the universal gas constant divided by molecular weight of B becomes specific gas constant Rb as shown over here. So, basically R upon molecular weight of m or universal gas constant R upon molecular weight of m will come as this R, which is specific gas constant. Similarly, I will do for gas A, similarly I will do for gas B. Why? In general, Ra is equal to universal gas constant R upon molecular weight of A, where universal gas constant is 8.314 joules per mole Kelvin. So, basically now I would like to express the have the earlier expression in terms of mass of gas A and mass of gas B also, all right. So, universal gas constant R and specific gas constant R are the universal gas constant and specific gas constant respectively. From the earlier slide, choosing the ideal gas equation in terms of gas mass, what we get is this. So, I am now writing PmVm is equal to mmRmTm. This is what we just saw. PV is equal to mRT, P1Bm is equal to MBRB into Tm. Dividing one over the other, I will get PmVm upon P1A Vm. Now, I can't cancel both R and T because Tm and Tm will get cancelled over here, Vm and Vm will get cancelled over here. What I get is Pm upon P1A is equal to mmRm upon MARA, which is nothing but 1 by Ya, because Pm upon P1A is 1 by Ya. We have just now earlier seen that. What does it mean? Same thing I am doing it for gas B, Pm upon P1B nothing but 1 upon Yb. So, what I get from here is equal to 1 upon Yb. Ultimately, I will get mmRm upon mm, MARA upon mm is equal to Ra into Ya. If I just rearrange this, I want an expression basically for this, which is what is figuring in my expression for work. Similarly, for gas B. So, putting all these things, Pm upon P1 is equal to 1 upon Ya, Pm upon P is equal to 1 upon Yb, and MARA upon mm is equal to RmYa, and MBRB mm is equal to RmYb. I will put this expression in my this expression which I had derived earlier, substituting all this. So, I will just replace Pm by P1A by 1 upon Ya, and here I will replace this. Similarly, I will replace this term by RmYa. Similarly, I will replace this term by RmYb. So, if I put those expressions, I will get this equation. So, Wi upon mm is equal to RmTm Ya log 1 by Ya plus Yb log 1 by Yb. The expression looks very simple now. I got a RT mixture temperature and Rm Ya upon 1 up log 1 upon Yb plus Yb log plus 1 upon into 1 by Yb, where PV is equal to, if I just replace by RmTm and mm here and want to convert it to the molar form, I can write work of separation per mole of gas mixture Wi by Nm, and here immediately universal gas constant will figure. Please understand this. Please understand the relationship between the universal gas constant and specific gas constant, because this is a work of separation per gram of mixture per mass basically, and this is a molar expression. So, you got a mass expression and a molar expression also. As soon as the molar expression comes here, universal gas constant comes. As soon as the mass comes over here, specific gas constant comes over here. So, the ideal work of separation per mole of mixture gas A, gas B will be given as the molar expression. Ideal work of separation per mole of mixture, that is Wi by Nm is equal to RTM Ya log 1 by Y plus Yb log 1 by Yb. This is for a mixture of gas A plus gas B. I can extend this to A, B, C or A, B, C, D. We can have different components in a mixture, and similarly I can show an expression for A, B and C mixtures. On the similar line, if the mixture is composed of 3 different gases, gas A, gas B and gas C, the ideal work of separation per mole of mixture is given by Wi by Nm RTM Ya log 1 by Ya plus Yb log 1 by Yb plus Yc log 1 by Cc. If you got a D, we will get Yd log 1 by Yd. What are Ya, Yb and Yc? It's a molar fraction of gas A, gas B and gas C in the mixture. What is Tm? Temperature of mixture, universal gas constant. So, this is basically work of separation of per mole of the mixture, work of separation per mole of mixture. What I am doing is basically find out work of separation is nothing but work done to compress each of these component gas A and gas B and gas C from their respective partial pressure to the mixture pressure, as we have seen in earlier reversible gas separation process. And this is what ideal work of gas separation will be. The actual work of separation, however, as you know, will be different, and therefore, we introduce a term in the next slide called figure of merit, which we have already introduced in a gas liquefaction also. So, generalizing the above equation for a mixture of n constituents, we just showed for A and B, we also showed for A, B and C, but if the mixture which has possibly has got n constituents, what will the formula be now? The formula will be Wi upon Nm, that is work of separation per mole of gas mixture is equal to RTM into sigma j is equal to 1 to n, sigma Yj log 1 upon Yj. So, if I got j is equal to 1 to 2, n is equal to 2, I get Y1 log 1 by Y1 plus Y2 log 1 by Y2 if 1 and 2 are respective gases. I can have n gases, and therefore, I can have log 1 upon Y1 plus Y2 plus Y3 plus Y3, same terms will repeat, and the summation of all this thing will give the work of separation per mole of gas mixture, where Yj is the mole fraction of the jth component. So, basically this sigma expression comes, normally we will have 2 component or 3 component or maximum 4 components, not more than that. So, from the same thing, this is the ideal work of separation. I define one more term, as I said earlier, similar to the liquefaction system, the figure of merit or FOM is also defined as figure of merit is equal to ideal work divided by actual work. The ideal work could be in molar basis or on a mass basis also. So, Wi by Nm divided by W by I by Nm. You know, the negative sign is basically the work done on the system, that is why. Similarly, Wi by mm, which is on a mass basis now, divided by actual work of separation. Actual work of separation must be much higher than the ideal work of separation, and therefore, the figure of merit will always be less than 1. So, this is what we have learnt. We have basically got an expression for work of separation. We understood what a figure of merit would be of a given system. So, just to summarize what we did in the first lecture of this topic of gas separation, I will just take you through some summary points. We just discussed different techniques employed for gas separation, which are synthetic membranes, adsorption, absorption and distillation. The separation can be done at both room temperature and cryogenic temperature. When I use room temperature technique, I use normally the method of adsorption, or I can use membranes, or I can use absorption, while the distillation normally done at cryogenic temperature. In an ideal system, all the processes are reversible, and the work requirement in an ideal gas separation is called ideal work. So, we just got an expression for ideal gas separation, work done in order to, or a work requirement for ideal gas or ideal work requirement for gas separation. And what is that expression? The ideal work requirement per mole of gas mixture to to separate a mixture with n constituents is given by this general formula. So, general formula tells you Wi by Nm is equal to RTM sigma Yj into log of 1 by Yj, when j is going from 1 to n constituents. N equal to 2, then and therefore, A and B are the two gases, then Ya log 1 upon Ya plus Yb into log 1 upon Yb, where Yj is the mole fraction of the jth component. We got a small self assessment exercise to given. Please go through that thing and kindly assess yourself for this. Based on whatever we have learnt in this lecture, I am devoting more time in the lecture 2 for solving tutorials, so that you understand the relevance of the formula which we have just derived in order to calculate the ideal work of separation. And this is a small self assessment test. Please go through it and assess yourself. There are answers given at the end. Thank you very much.